What if we've just pierced the invisible veil around an interstellar stranger hurtling through our solar system? Right now, something from another star system is moving through our neighborhood, and for the first time in human history, we've seen it in a way no one ever has before. We've caught it glowing in X-ray wavelengths that required cutting-edge technology to detect, revealing secrets it's carried across the galaxy. A Japanese satellite, floating in the silence of space, turns its gaze toward this cosmic visitor. It's not looking with normal eyes. It's peering into the X-ray spectrum, a realm of light so energetic, so invisible to our human senses, that most objects in space remain hidden there. But when JAXA's XRISM satellite locked onto Comet 3I Atlas, something extraordinary happened. A faint glow materialized around it, a halo of X-ray light that wrapped the visitor like a ghostly shroud. Early XRISM analysis suggests 3I Atlas may show subtle spectral differences from solar system comets still under study by researchers, let alone one that came from the depths between the stars. Is this the hidden face of a cosmic traveler? Or have we stumbled upon something our eyes, our technology, our very understanding of the universe was never meant to witness until this precise moment? The implications send shivers down my spine, and I think they will yours too once you understand what we're really looking at here. How does solar wind crashing into escaping gas create light we can't normally see? Why did JAXA choose this exact window of time to observe? What buried secrets does this X-ray glow hold about where 3I Atlas truly originated, what it experienced in the void between stars, and what it might tell us about worlds we'll never visit in our lifetimes? These questions aren't just academic curiosities. They're doorways into understanding our place in a universe that's far stranger and more interconnected than we ever imagined. Stick with me, friend. In the next minutes, we're diving deep into the first X-ray image of an interstellar visitor that reveals something we've never seen before. We're going to unpack the science, yes, but more importantly, we're going to explore what this means for you, for me, for everyone who's ever looked up at the night sky and felt that ache of wonder. We're going to trace the journey from a team of dedicated scientists in Japan to this moment right now where you and I are connecting over a discovery that rewrites what we thought we knew about visitors from other star systems. This isn't just about a comet. It's about the universe reaching out and showing us that there's always more to discover, always another layer of reality waiting just beyond what our senses can perceive. If this sends chills down your spine the way it does mine, do me a favor right now. Hit that like button. It tells me you're as captivated by this mystery as I am. And drop a comment telling me where you're watching from, whether you're under dark country skies where you can actually see the stars or in a city where light pollution hides them. Your perspective matters because we're all part of this story. We're all witnesses to a moment in history where humanity took one more step toward understanding the cosmos. Every view, every like, every comment fuels this journey of discovery we're on together. So let's dive in and uncover what this X-ray stranger is really showing us. Now, before we get into the technical details that make this discovery so profound, I want you to understand something fundamental. We've known for a while now that objects from interstellar space occasionally visit our solar system. The first confirmed one was Oumuamua, that strange elongated visitor that sparked debates about whether it could be artificial. Then came Comet Borisov, more comet-like and familiar. And now we have 3I Atlas, adding to this small but growing family of interstellar wanderers. But here's what's different. What makes this moment historic? We've never captured one of these visitors in X-ray light before. Never. Not once in the entire history of astronomy have we seen what an interstellar object looks like when you peer at it through X-ray eyes. Why does that matter? Because X-rays reveal processes and structures that remain completely invisible in normal light. When you look at 3I Atlas with an optical telescope, you see a fuzzy blob, maybe a tail if conditions are right. Standard comet stuff. But when JAXA's XRISM satellite turned its specialized X-ray imager toward this visitor, it revealed a glowing halo of high-energy light surrounding the nucleus, extending outward in a pattern that tells a story about interactions happening at the atomic level. This glow comes from something called charge exchange, a process where solar wind particles strip electrons from atoms in the comet's outgassing material, releasing X-ray photons in the process. It's like watching the solar wind paint an invisible picture around the comet, a picture that only X-ray detectors can see. But here's where it gets really interesting, where my mind starts racing with possibilities. The X-ray signature from 3I Atlas doesn't quite match what we've seen from solar system comets. There are subtle differences in the spectral lines, in the distribution of the glow, in how it responds to solar wind pressure. These differences might seem small, technical, the kind of thing only specialists care about, but they're not. They're clues. They're fingerprints of a different origin, a different history, a different chemical composition shaped by formation conditions around another star. This comet carries the signature of a place we've never been, a stellar nursery perhaps thousands of light years away, and now we're reading that signature for the first time in X-ray wavelengths. Can you feel the weight of that? We're not just observing a comet, we're reading a message written in atoms, delivered across the galaxy, now glowing before our instruments in colors our eyes can't see. And the message is clear. The universe is more diverse, more varied, more full of subtle differences than we ever grasped when we could only study objects born around our own Sunday. This is what discovery feels like. This is what it means to push the boundaries of human knowledge, one observation at a time. And you're here for it, right at the beginning of understanding what this X-ray glow really means. So let's go deeper together. By the end of this journey, you'll never look at the night sky quite the same way again. Picture a team of quiet geniuses working in research centers across Japan, their eyes fixed on data streams coming from a satellite they've spent years designing and building. These aren't the flashy celebrities of science you see on television. They're the dedicated specialists, the ones who understand X-ray spectroscopy the way a musician understands their instrument. They built XRISM, the X-ray imaging and spectroscopy mission, with one clear purpose: to resolve the universe's faintest glows with unprecedented clarity, to catch whispers from the void that other telescopes miss entirely. XRISM launched with a suite of instruments designed to observe the cosmos in soft X-ray wavelengths, the lower energy end of the X-ray spectrum, where many astronomical processes reveal themselves. The Extend Imager, one of XRISM's primary tools, has a wide field of view and the sensitivity to detect extremely faint X-ray emissions. It's like having the most sensitive microphone in a silent room, able to pick up the softest breath. When word came that 3I Atlas was making its way through the inner solar system, these researchers recognized an opportunity that might not come again in their careers. An interstellar visitor, close enough to observe, active enough to be outgassing, and positioned where XRISM could point its instruments without interference from Earth or the Sunday. This was the perfect storm of circumstances. So they did what scientists do best. They planned. They calculated observation windows. They submitted proposals and convinced review committees that this was worth precious satellite time. And then they waited, because space observations require patience. You can't rush a satellite into position. You can't force the universe to cooperate with your schedule. You prepare, you point, and you hope that when the data arrives, it tells you something new. When 3I Atlas streaked closer to the Sun through November, reaching its closest approach, and then heading back out toward the outer solar system, XRISM was ready. The team commanded the satellite to lock its gaze on the comet's position. For days, the Extend Imager stared into what looked like empty space to human eyes, collecting photons one by one, building up an image from the faintest trickle of X-ray light. This is how modern astronomy works. It's not the dramatic moment of putting your eye to a telescope and gasping at what you see. It's the slow accumulation of data, the patient gathering of evidence, the careful analysis that follows. It's less like discovering treasure and more like archaeology, brushing away dust grain by grain to reveal something ancient and precious. And then, in the analysis room, as the data processing algorithms did their work, it happened. A soft X-ray halo flickered into existence on their screens. The glow was faint, spread out across the field of view, but unmistakable. X-ray photons were coming from the region around 3I Atlas. This wasn't noise. This wasn't an artifact. This was real. The team knew immediately they were seeing something historic because this signature, this particular pattern of X-ray emission, had never been captured from an interstellar object before. The X-rays came from charge exchange, a process that scientists had predicted but never observed in this context. Here's how it works, and stay with me because this is beautiful in its elegance. The Sun constantly blasts a stream of charged particles into space, mostly protons and electrons moving at tremendous speeds. This is the solar wind, and it fills the entire solar system. When these high-energy particles encounter neutral atoms, like the oxygen, carbon, and nitrogen that comets release as they outgas near the Sun, something remarkable happens. The solar wind ions are hungry for electrons, and they steal them from the neutral atoms in a process called charge exchange. When this electron capture occurs, the ion drops into an excited state and then relaxes, releasing the excess energy as an X-ray photon. The result is an X-ray glow that traces the interaction between solar wind and cometary outgassing, painting an invisible picture in high-energy light. JAXA's team watched this process unfold in their data. They saw the spectral signatures of carbon, nitrogen, and oxygen lighting up in X-rays, confirming that charge exchange was actively happening around 3I Atlas. The detail that transforms this from a successful observation into something potentially profound. Why does this particular visitor produce such a clear, extended X-ray halo? Regular comets from our solar system do emit X-rays through the same charge exchange process. Scientists have known about that since the discovery of cometary X-ray emissions decades ago. But there's something about 3I Atlas's X-ray signature that feels different, that doesn't quite match the pattern we're used to seeing. Is it outgassing more efficiently because its ice is formed under different temperature conditions around another star? Is the composition of its volatiles subtly different, leading to variations in how charge exchange proceeds? Or is there something about its structure, its nucleus, the way it responds to solar heating, that sets it apart from the local comets we've studied for generations? These questions don't have easy answers yet. The data is still being analyzed, papers are still being written, and the scientific community is still digesting what XRISM has shown them. But the questions themselves are thrilling because they point toward a deeper truth. Every interstellar visitor is a laboratory, a natural experiment that tests our understanding of how planetary systems form around different stars. The JAXA team didn't just make an observation, they opened a door. They showed that X-ray astronomy can be a powerful tool for characterizing interstellar objects, adding a completely new dimension to how we study these rare visitors. Before XRISM's observation, we relied on visible light, infrared, maybe radio wavelengths to understand interstellar comets. Now we have X-rays in our toolkit, and that means we can ask questions we couldn't even formulate before. What does the X-ray spectrum tell us about the isotopic ratios in the comet's ices? How does the spatial distribution of the X-ray glow relate to the structure of the coma? Can we use X-ray timing to track variations in outgassing as the comet rotates? These aren't abstract academic questions. They're pathways to understanding the diversity of planetary systems in our galaxy. Every piece of data we extract from 3I Atlas is a clue about conditions somewhere else, sometime in the past, around a star we may never identify. It's cosmic forensics, and the JAXA team just handed us a new forensic technique that works in wavelengths we couldn't access before with this kind of precision and clarity. So when you hear about this X-ray image, remember the people behind it. Remember the years of planning, the technical brilliance required to build instruments sensitive enough to detect these faint glows, the dedication it takes to turn raw satellite data into scientific understanding. They're the silent watchers, the ones who expand human knowledge, one careful observation at a time. And what they've given us with this image is nothing less than a new way of seeing the universe. But observation is only the beginning. The real question is what that observation means, and to understand that, we need to go deeper into what X-rays can tell us that visible light cannot. We've chased comets for centuries with every trick and tool we could devise. Optical telescopes were the first, of course, allowing astronomers to plot orbital paths and study the visible glow of Comets tails. Then came photography. Spectrographs that could break light into its component colors and reveal chemical compositions. We added infrared observations to detect heat and study dust, radio telescopes to track molecular emissions from outgassing, ultraviolet instruments to catch the signatures of certain atoms excited by sunlight. Each new wavelength added another layer of understanding, another perspective on what comets are and how they behave. But X-rays? That's a different category entirely. That's piercing deeper than any of those other techniques, catching high-energy dances that our eyes ignore completely and that the Earth's atmosphere blocks entirely from ground-based observation. X-ray astronomy had to wait for the space age because you can't do it from the ground. The atmosphere absorbs X-rays before they reach the surface, which is fortunate for life on Earth but frustrating for astronomers. So we launched X-ray telescopes into orbit, and we started seeing the universe in a completely new light, discovering phenomena that were invisible in every other wavelength. Hot gas in galaxy clusters, matter swirling into black holes, the high-energy activity in stellar coronae, supernova remnants glowing with the heat of their violent births, all revealed in X-ray wavelengths. And now, for the first time, We're applying that X-ray vision to an interstellar visitor, and what we're seeing is extraordinary in its detail and its implications. JAXA's XRISM satellite, with its soft X-ray imager, caught the glow spreading wide around 3I Atlas, a halo born from atoms stripping electrons in solar wind collisions. This isn't a reflection of sunlight. It's not thermal emission from hot dust. It's a fundamentally different process, a fluorescence that happens at the atomic level when high-energy particles interact with neutral gas. And the beauty of X-ray spectroscopy is that it doesn't just show you that something is glowing. It tells you exactly what's glowing and why. The spectrum XRISM, captured from 3I Atlas, showed clear emission lines from carbon, nitrogen, and oxygen. These are the fingerprints of charge exchange, the signature that confirms solar wind ions are grabbing electrons from these atoms in the cometary coma. But look deeper at what that means. Carbon, nitrogen, oxygen, these are the building blocks of life as we know it. They're the elements that form amino acids, nucleotides, the organic molecules that eventually led to you and me sitting here having this conversation across space and time. And here they are, glowing in X-rays, coming from an object that formed around another star, possibly in a molecular cloud light years away, now passing through our solar system and showing us its chemical composition in the most dramatic way possible. When I think about that, when I really let it sink in, it fills me with a sense of connection that's hard to put into words. The carbon in your body, the nitrogen in your DNA, the oxygen in the air you're breathing right now, all of it was forged in stars and scattered into space when those stars died. And here's 3I Atlas, carrying its own cargo of those same elements, formed in a different stellar nursery, but made of the same cosmic stuff. We're all stardust, as Carl Sagan famously said. And this X-ray glow is literal proof of that connection, playing out before instruments we built to see the invisible. But it's not just the presence of these elements that matters. It's the ratios, the relative abundances, the subtle variations in how they're distributed in the coma. When scientists compare the X-ray spectrum from 3I Atlas to what they've seen from solar system comets, they notice differences. The emission lines have slightly different intensities, suggesting different relative abundances of carbon, nitrogen, and oxygen. The spatial distribution of the X-ray glow doesn't quite match the models built from observations of comets born around our Sunday. These are small differences, technical details that require careful analysis to even detect, but they're significant because they hint at formation conditions that weren't quite the same as what we experience in our solar system. Think about what that implies. When our solar system formed from a collapsing molecular cloud, the temperature, pressure, and chemical composition of that cloud determined what kinds of planets, asteroids, and comets would eventually coalesce. The ices that froze into comets in the outer reaches of our protoplanetary disk had a particular composition, a particular set of isotopic ratios, because they formed under those specific conditions. But 3I Atlas, it formed somewhere else, in a different molecular cloud or a different part of a cloud, around a different star that might have been hotter or cooler, more massive or less massive than our Sunday. The conditions were different, and so the chemical fingerprint is different, not radically different. These are still the same elements we know and love, but different enough that when you look carefully, when you peer into X-ray wavelengths and analyze spectral lines with the best instruments humanity has built, you can see it. This is what X-ray observations give us that visible light cannot. Visible light shows us the dust, the reflected sunlight, the overall brightness and color. It's a surface-level view, beautiful and informative, but limited. X-rays cut through to the interactions happening at the atomic level, revealing the processes that energize the coma, the composition of the outgassing material, the dynamics of how solar, wind, and cometary gas mix and exchange particles. It's like the difference between looking at a painting and analyzing the chemical composition of the paint. Both tell you something, but they're answering completely different questions. Yet experts whisper, in conference hallways and in the comment sections of preprint papers, that this halo's shape and its steady pulse through varying solar wind conditions don't quite match what we've come to expect from solar system norms. There's something about the way the X-ray emission tracks with solar wind intensity that's slightly off from the models. Is 3I Atlas shedding gases at a different rate than local comets do at similar distances from the Sun? Is the nucleus structure different, perhaps more porous or more compact, affecting how heat penetrates and drives out gassing? Or is there something about the chemistry itself, the way these particular ices sublimate and release their atoms into space, that creates a different interaction regime with the solar wind. I want to be clear here. No one is suggesting anything wild or speculative like artificial origins or alien technology. This is science proceeding carefully, noting observations that don't quite fit expectations and working to understand why. That's how progress happens. You observe something unexpected, you check your instruments to make sure you're not seeing an error, and then you start building new models that can explain what you're seeing. The JAXA team and the broader scientific community are in that phase right now with 3I Atlas's X-ray data. They're asking good questions, running simulations, comparing with other comets, and slowly building a more complete picture of what makes this interstellar visitor unique. But here's what gets me, what keeps drawing me back to this story. Every unexpected detail, every small deviation from the norm, is a piece of evidence that the universe is richer and more varied than we've mapped so far. We've studied dozens of comets from our solar system in detail. We have a good sense of their average properties. And now we have exactly 3 confirmed interstellar objects to compare them to: Oumuamua, Borisov, and 3I Atlas. 3. That's a tiny sample size. Each one has surprised us in different ways. Oumuamua with its strange acceleration and elongated shape, Borisov with its surprisingly familiar comet-like behavior but different carbon monoxide to water ratio, and now 3I Atlas with its X-ray glow that doesn't quite fit the mold. What will the 4th interstellar visitor show us? Or the 10th? Or the 100th? We're at the very beginning of studying objects from beyond our solar system, and already we're seeing diversity that challenges our comfortable assumptions. That's exactly where we want to be as a species seeking to understand the cosmos. Not confirming what we already know, but pushing into territory where the answers aren't clear yet, where observations raise new questions, where each discovery opens doors we didn't even know were there. The X-ray view of 3I Atlas is one of those doors, and what lies beyond it is a whole new way of studying interstellar objects that combines chemistry, plasma, physics, atomic processes, and comparative planetology all in one glowing package. This is astronomy at its best, using every wavelength we can access, every instrument we can build, to squeeze understanding out of rare and fleeting opportunities. Because that's what 3I Atlas is, a fleeting opportunity. It came, it glowed, and soon it will be gone, racing back into the darkness between stars, carrying its secrets with it except for what we managed to capture in these precious observations. So when you hear scientists say this X-ray image reveals something we've never seen before, understand that it's not hyperbole. It's literal truth. We have never seen an interstellar object in X-ray wavelengths until XRISM pointed at 3I Atlas and captured this glow. And now that we have, now that we know it's possible, and we know what to look for, we'll be ready for the next visitor. We'll have better instruments, better models, and better questions. That's the gift this observation gives us. Not just the data itself, but the roadmap for how to study future interstellar visitors in ways we couldn't imagine before. And that roadmap leads us straight into understanding the next crucial piece of this story, the timing and conditions of the observation itself. Late November, when most people in the Northern Hemisphere are thinking about holidays and cold weather settling in, the XRISM team was focused on something far more celestial. Comet 3I Atlas had just passed its closest approach to the Sun earlier in the season, and it was now in that perfect window where it was still active, still outgassing significantly, but far enough from the Sun's glare that XRISM could observe it without overwhelming interference. Timing in astronomy is everything. You can have the best instruments in the world, but if you point them at the right target at the wrong time, you get nothing. The JAXA researchers understood this intimately. They had been tracking 3I Atlas's trajectory for months, calculating optimal observation windows, coordinating with other telescopes, conducting simultaneous observations in different wavelengths. This wasn't a spur-of-the-moment decision. This was the culmination of careful planning that accounted for satellite pointing constraints, solar avoidance angles, the predicted outgassing activity level of the comet, and competition for telescope time with dozens of other worthy projects. Space-based observatories like XRISM are in constant demand. Every astronomer has targets they want to observe, and only a small fraction of proposals get approved. The fact that this observation happened at all is a testament to the scientific importance the review committees saw in studying an interstellar object with X-ray instruments. When XRISM finally locked onto 3I Atlas, it maintained that lock for extended periods. allowing the extend imager to collect photons over many exposures. Think of it like long exposure photography. If you want to capture a faint object, you need to gather as much light as possible, and that means pointing your camera or telescope at the target and waiting. In X-ray astronomy, this waiting can take days because X-ray photons from distant or faint objects arrive at such a slow trickle that you need immense patience to build up enough signal to distinguish real emission from background noise. The team programmed the satellite to take multiple exposures, slewing back to 3I Atlas's position repeatedly as the comet moved against the background stars, ensuring they captured as much of the X-ray glow as the satellite's precious observation time would allow. And then came the moment every astronomer lives for. The first images dropped, not to the public, not yet, but into the analysis pipelines, where specialists began processing the raw data. What they saw must have sent a ripple of excitement through the team. A sprawling X-ray cloud surrounding the comet's position, diffuse but unmistakable, extending across the field of view like a ghostly halo. The intensity was low, exactly what you'd expect from charge exchange emission, but the spatial extent was impressive. This wasn't a point source. This was an extended structure, a three-dimensional interaction region where solar wind and cometary outgassing met and produced light in wavelengths invisible to human eyes. The confirmation that they were seeing charge exchange emission came from the spectrum. When you split X-ray light into its component energies, just like a prism splits white light into a rainbow, you see emission lines at specific energies corresponding to specific atomic transitions. The XRISM data showed those lines clearly. Carbon's characteristic X-ray emission at certain energies, nitrogen at others, oxygen contributing its own signature. These spectral fingerprints are unmistakable. They tell you exactly what elements are present and what processes are exciting them. In this case, the spectral patterns match charge exchange predictions perfectly, confirming that solar wind ions were capturing electrons from cometary atoms and emitting X-rays in the process. But here's where it gets fascinating from a detective's perspective. The spectral lines appeared sharper and cleaner than some past solar system comet observations. XRISM's advanced technology contributes significantly better signal-to-noise ratio. Some of this is certainly due to XRISM's superior instrumental capabilities. The satellite represents the latest generation of X-ray spectroscopy technology, with better energy resolution and sensitivity than older missions. But not all of it can be explained by better instruments. Some of the clarity might be intrinsic to 3I Atlas itself, reflecting a different composition or outgassing behavior that produces a cleaner charge exchange signal. Astronomers felt it viscerally as they pored over the data. This wasn't routine. This was history unfolding in spectra and images, a first that they got to be part of. Whispers spread through the community even before formal announcements, the way they always do when something significant happens. Conference presentations were updated. Draft papers were circulated among colleagues for feedback. Social media accounts run by science communicators started teasing exciting news about XRISM and 3I Atlas. And then came the official announcements, carefully worded to convey both the excitement and the scientific rigor. First interstellar object observed in X-rays. Charge exchange detected. Spectral analysis reveals composition. These aren't flashy headlines, but to those who understand the context, they're earth-shattering. Think about the chain of events that had to align for this observation to happen. First, 3I Atlas had to exist, and had to pass through our solar system on a trajectory that brought it close enough to the Sun to become active. That alone is rare. We've only confirmed 3 interstellar visitors ever. Second, XRISM had to be operational, having launched successfully and completed its commissioning phase. Space missions fail more often than we'd like to admit, so this wasn't guaranteed. Third, the XRISM team had to recognize the opportunity and submit a successful proposal to observe. Fourth, the observation had to actually work. The satellite had to point correctly. The instruments had to function. The data had to download successfully. Any one of those steps could have failed, and we wouldn't have this historic image. But it all came together, and what that team captured extends far beyond just the immediate data. They captured a moment of possibility, a demonstration that X-ray astronomy can contribute meaningfully to the study of interstellar objects. Before this observation, that was theoretical. We thought charge exchange should produce detectable X-rays from interstellar comets, but we'd never proven it. Now we have. We know the technique works. We know what the signals look like, we know how to interpret the data, and that knowledge becomes the foundation for future studies, better proposals, improved instruments, and deeper understanding. The images themselves, when you look at them, are beautiful in an austere, scientific way. They're not Hubble's glorious full-color vistas. They're false-color representations of X-ray intensity, often rendered in cool blues and purples to indicate the high-energy photons being detected. The background is mostly dark, with occasional bright pixels marking X-ray sources in the field of view. And there, spread across multiple pixels, fainter than the brightest sources but clear and definite, is the glow around 3I Atlas. It's subtle. If you didn't know what you were looking for, you might miss it. But to the trained eye, to the researchers who spent years learning to read X-ray data, it's a revelation. The halo hugged the coma like a shroud. Those are the words that keep coming back to me. A shroud, something that covers and conceals, but also something that in being revealed shows what was hidden. For the entire journey of 3I Atlas, from its unknown origin star system to our solar system, this X-ray glow was there, potential, waiting for the right conditions and the right observer. When the comet was in deep space, far from any star, there was no solar wind to trigger charge exchange and no X-ray emission, silent and dark. But as it fell sunward, as our star's breath reached it and began stripping atoms from its sublimating ices, the glow ignited. And we were there with the right instrument at the right time to catch it. That's not luck. That's the result of decades of investment in space-based astronomy, in X-ray detector technology, in the hard work of scientists who dream of moments like this and then make them happen through skill and determination. So, when I talk about this historic gaze, I'm not just referring to a satellite looking at a comet. I'm talking about humanity reaching out across the void, using technology we built with our own hands and minds to see something no human had ever seen before. Every great observation in astronomy is a victory, not just of science, but of curiosity and persistence. And this one, this X-ray portrait of an interstellar stranger, ranks among the most significant because it opens a new chapter in how we study the universe beyond our solar system. But to really appreciate why this matters, we need to understand how 3I Atlas compares to everything else we've ever studied. Think back to Oumuamua, that strange visitor that sparked global fascination and more than a little speculation. It entered our solar system, accelerated in ways that couldn't be fully explained by cometary outgassing alone, and left without giving us many answers. We got visible light observations that showed an elongated shape, possibly tumbling, but that was about it. By the time we realized what it was already leaving, and it never showed clear signs of a coma or tail. Was it a comet, an asteroid, something else entirely? The debates continue because we didn't have enough data, and critically, we didn't catch it in wavelengths that could reveal its composition or activity level definitively. X-rays? Silent? If Oumuamua was producing X-ray emission through charge exchange or any other process, we never detected it, likely because it wasn't active enough or we weren't looking in the right way at the right time. Then came Borisov, designated 2I, Borisov, and it felt like a relief to astronomers. Finally, an interstellar visitor that looked like a comet, behaved like a comet, and gave us time to study it properly. Telescopes around the world trained on Borisov, capturing spectra that showed it was outgassing carbon monoxide and water, confirming it was made of ices similar to comets from our solar system. But even Borisov had its surprises. The ratio of carbon monoxide to water was higher than typical for solar system comets, suggesting it formed in a colder environment or from different starting materials. It was familiar yet different, a theme that keeps repeating with these interstellar visitors. We recognize them as comets, but they carry subtle signatures of their foreign origins. And now we have 3I Atlas, and with it we have X-ray data, a completely new dimension of information that neither Oumuamua nor Borisov provided. So how does it compare? Start with the basics. 3I Atlas is clearly a comet. It has a coma. It's outgassing as it approaches the sun. It's behaving exactly as you'd expect a comet to behave in terms of visible light observations. But when you add the X-ray view, suddenly you have access to information about the atomic level interactions happening in the coma, and that's where the differences start to become apparent. The X-ray halo around 3I Atlas pulses with solar wind rhythm, intensifying and fading as the density and velocity of the solar wind varies. That's expected. Solar wind drives charge exchange, so stronger solar wind should produce more X-rays. Solar system comets show the same behavior, but what specialists are noticing is how steady the emission remains through those variations, how the spatial distribution of the X-ray glow doesn't fluctuate as wildly as models predict. It's as if the charge exchange process around 3I Atlas is more stable, more buffered against solar wind variations than what we typically see. Why would that be? One possibility is that the outgassing rate from 3I Atlas is steadier than from solar system comets. If the nucleus is releasing gas at a more constant rate, that would provide a more uniform target for solar wind particles to interact with, smoothing out the X-ray emission variability. But what would cause steadier outgassing? Perhaps the nucleus has a different structure, maybe more homogeneous in composition, or more uniformly porous, allowing heat to penetrate and drive sublimation more evenly across the surface. Or perhaps the types of ices present sublimate at rates that are less sensitive to small temperature fluctuations. Another possibility lies in the composition itself. The spectral lines XRISM detected show carbon, nitrogen, and oxygen, but the relative intensities of those lines carry information about the relative abundances of those elements in the coma. When researchers compare the line ratios from 3I Atlas to those from well-studied solar system comets, they see differences. Not huge differences, we're still talking about the same elements in roughly similar proportions, but measurable differences that suggest the chemical makeup isn't identical. Maybe 3I Atlas formed in a region of its birth molecular cloud where nitrogen was slightly more abundant, or where carbon froze out more efficiently. These differences would be set billions of years ago when the comet first coalesced, and they'd persist unchanged through its entire journey to our solar system. There's also something compelling about how clean the spectral lines are. Less clutter, more definition. Part of this is definitely XRISM's superior instruments, but could some of it be intrinsic? Could 3I Atlas have fewer contaminants, less dust mixed with its ices, resulting in cleaner charge exchange signals? Dust can complicate X-ray observations because it absorbs and scatters X-rays, muddying the spectral lines. If 3I Atlas is relatively dust-poor compared to solar system comets, that would explain some of the spectral clarity. And why might it be dust-poor? Perhaps because it formed farther from its parent star, in colder regions where dust grains were less efficiently incorporated into growing comet nuclei. Or perhaps its long journey through interstellar space exposed it to erosion processes that preferentially removed surface dust layers. I want to pause here and address something that inevitably comes up whenever we discuss interstellar objects behaving differently than expected. Online, in forums and comment sections, you'll find claims about artificial origins, alien technology, intentional probes sent to explore our system. These ideas are exciting to think about, and they make for great science fiction, but they're not supported by the data we actually have. The XRISM observations of 3I Atlas are entirely consistent with natural cometary processes. Charge exchange is a well-understood phenomenon. The spectral lines match atomic physics predictions. The spatial distribution makes sense given outgassing and solar wind interaction models. There's no need to invoke extraordinary explanations because ordinary astrophysics, applied to an object from a different stellar system, explains what we're seeing perfectly well. But here's what's genuinely thrilling. Even within the framework of natural processes, 3I Atlas is teaching us that ordinary covers a much wider range of behaviors and compositions than we'd mapped from studying only solar system objects. The universe isn't uniform. Different star systems form under different conditions, from molecular clouds with different chemical compositions, around stars of different masses and temperatures. The comets that form in those systems will reflect those differences, and when they occasionally get ejected and wander into our neighborhood, they bring those differences with them. Each interstellar visitor is a sample from somewhere else, a data point that expands our understanding of the diversity of planetary system formation. Some researchers are already speculating about what these compositional differences might tell us about 3I Atlas's origin. If the nitrogen-to-carbon ratio is elevated, that might point toward formation in a very cold molecular cloud where nitrogen ices could condense efficiently. If oxygen is less abundant than expected, perhaps the comet formed closer to its star where warmer temperatures limited oxygen incorporation. These are educated guesses, hypotheses that future observations and modeling work will test. But they're grounded in real data, in those spectral lines that XRISM captured, in the differences that careful analysis is revealing. And here's where I get excited about the future. We now have a baseline. We have detailed X-ray observations of one interstellar comet, 3I Atlas. When the next interstellar comet comes, and there will be a next one, maybe not this year or next, but eventually, we'll be able to compare it to 3I Atlas. We'll be able to ask, is this new visitor's X-ray signature similar or different? Do they share compositional traits suggesting they came from similar environments, or are they distinct, pointing to formation in very different conditions? Over time, as we accumulate observations of more interstellar objects, we'll start to build a statistical picture of the diversity out there. We'll be able to say things like, most interstellar comets seem to have higher carbon monoxide ratios, or nitrogen abundances in interstellar visitors cluster around certain values. That statistical understanding will, in turn, inform models of planetary system formation throughout the galaxy. This is how science progresses, not through single revolutionary observations that answer every question, but through the slow accumulation of data points, each one refining our understanding, each one constraining the possibilities, until the picture becomes clearer and clearer. 3I Atlas is one of those data points, perhaps the most valuable one we have right now in the X-ray domain, but it won't be the last. And every future observation will be informed by what we learned from this historic first X-ray image. The JAXA team didn't just capture a pretty picture. They established a methodology, proved a concept, and showed the world that X-ray observations of interstellar objects are not just possible, but scientifically rich with information. So when you think about 3I Atlas and its echoes of difference, don't think of it as strange or anomalous in a worrying way. Think of it as wonderfully diverse, as evidence that the universe is far more varied than we could discover by studying only our local neighborhood. Think of those subtle differences in spectral lines, in X-ray halo behavior, in outgassing patterns, as whispers from another star system, encoded in atoms and light, delivered across light years, and now decoded by human ingenuity. That's the real story here, not aliens or mysteries in the sensational sense, but the profound mystery of diversity in a cosmos that keeps surprising us with how much there is to learn. And speaking of learning, those spectral lines carry even more secrets than we've discussed so far, secrets written in the language of chemistry. Those spectral lines, when you really think about what they represent, are almost poetic in their significance. Carbon for diamonds and graphite, for the organic molecules that form life. Nitrogen for the atmosphere you're breathing, for the proteins that build your body. Oxygen for water, for the air, for the chemistry that makes Earth habitable. These aren't exotic elements. They're the mundane building blocks of everything we know, and yet seeing them light up in X-rays from an object born around another star carries an emotional weight that's hard to describe. Charge exchange lit them up, revealed them, made them visible in wavelengths that otherwise would have kept them hidden. Here's the process again, because it's worth understanding deeply. The sun emits solar wind constantly, a stream of charged particles, mostly protons and electrons, that flows outward at speeds that make a hurricane look still. This wind fills the solar system and continues outward, past the planets, past the Kuiper belt, until it finally runs into the interstellar medium and forms the heliosphere boundary. When 3I Atlas came close enough to the sun, it entered the thick part of this solar wind stream. As the comet heated up, its ices began to sublimate, releasing neutral atoms and molecules into space, forming the coma, that fuzzy cloud of gas and dust surrounding the nucleus. Now you have two populations of particles in close proximity, high-energy solar wind ions moving at tremendous speeds and relatively slow-moving neutral atoms from the comet. When a fast-moving solar wind ion collides with a neutral atom, it can steal an electron from that atom in a fraction of a second. This electron capture leaves the solar wind ion in an excited state, with the captured electron in a higher energy orbital than it wants to be. Almost immediately, the electron drops down to a more stable, lower energy state, and the excess energy gets released as a photon. The energy of that photon is in the X-ray range, specifically soft X-rays, and the exact energy depends on which atom was involved and which electron transition occurred. Carbon atoms produce X-rays at certain characteristic energies, nitrogen at others, oxygen at still others. It's like a fingerprint, unique and unmistakable. XRISM's spectrometer split those X-ray photons by energy and counted how many arrived at each energy level. The result is a spectrum, a graph showing intensity versus energy, and in that graph you see peaks at the energies corresponding to carbon, nitrogen, and oxygen emission lines. These peaks are the whispers from the spectrum, the direct evidence of what elements are present in the coma of 3I Atlas. And unlike some other observational techniques that require complex modeling to infer composition, X-ray spectroscopy is direct and unambiguous. If you see the carbon line, carbon is there. If you see the nitrogen line, nitrogen is there. It's beautifully straightforward. But it's what those elements mean in context that elevates this from simple chemical detection to something profound. These are biogenic elements, the ones essential for life as we know it. Now, I'm not suggesting 3I Atlas harbors life or carried life from another star system. There's no evidence for that, and the conditions in and on a comet nucleus are extremely harsh, cold, and not conducive to biological processes. But what I am saying is that the chemistry of life, the elemental building blocks, are universal. They're here on Earth, they're in the Sun, they're in interstellar molecular clouds, and they're in comet 3I Atlas from another star system. Wherever you go in the universe, these elements are present because they were forged in stars and distributed by supernovae and planetary nebulae throughout galaxies. The philosophical implication is staggering when you sit with it. We are not separate from the cosmos. We are made of the same stuff as interstellar comets. The atoms in your hand right now, reading this or holding your device, those atoms were once inside stars. They've traveled through space, condensed into planets and comets, and eventually found their way into you. And 3I Atlas, this visitor from beyond, carries atoms that went through a similar process around a different star, and now they're glowing in X-rays that we detected, completing a circle of observation that connects us across light years and billions of years of cosmic history. Unlike local comets, whose formation we can model with reasonable confidence because we understand the solar nebula conditions, 3I Atlas's chemical mix hints at colder birthplaces or different molecular cloud chemistry. The precise ratios of carbon to nitrogen to oxygen, extractable from the intensities of those spectral lines, don't quite match the average we've measured from solar system comets. They're close, well within the range of possibility for natural cometary composition, but shifted enough that it's noticeable. What does that shift tell us? It says that the molecular cloud or protoplanetary disk that 3I Atlas formed from had a slightly different chemical inventory than the one that formed our solar system. Maybe that cloud was enriched in nitrogen from a particular generation of stars that exploded nearby. Maybe the temperature gradient in the disk was different, affecting which compounds could condense at which distances from the star. This is the kind of detective work that gets astronomers excited, piecing together a history from indirect clues. We'll never visit the star system where 3I Atlas formed. We don't even know which star that is, but we can read the story written in its atoms. Every element, every isotope, if we could measure them with enough precision, is a clue about the conditions that prevailed there. And the X-ray spectrum, by revealing these elements so clearly through charge exchange, gives us one of the best windows into that story that we've ever had from an interstellar object. There's a researcher whose name keeps coming up in discussions of interstellar visitors, R.V. Loeb, who has gained notoriety for suggesting that some of these objects might have artificial origins. He's a serious scientist, but his ideas are controversial and not widely accepted by the astronomical community. I mention him because in the context of 3I Atlas, some of his followers and others in online spaces have speculated about whether the unusual X-ray properties could indicate something non-natural. The answer, to be absolutely clear, is no. The X-ray emission from 3I Atlas is entirely consistent with charge exchange from cometary outgassing. The spectral lines match laboratory measurements and theoretical predictions for how carbon, nitrogen, and oxygen atoms interact with solar wind ions. There's nothing in the data that requires or even suggests an artificial origin. But here's what's interesting about that speculation from a sociological perspective. It reveals how hungry we are as a species to find evidence of intelligence beyond Earth, how ready we are to leap to that conclusion, even when the data doesn't support it. And that hunger isn't wrong. It's beautiful in its own way. It speaks to our deep desire for connection, for knowing we're not alone in the universe. But good science requires discipline, requires that we follow the data where it leads rather than where we want it to go. And the data from XRISM leads clearly to natural cometary processes producing X-rays through well-understood physics. No mysteries that can't be explained. No need for exotic hypotheses. What is genuinely mysterious and thrilling, though, is the diversity those natural processes reveal. Even within the framework of comets and asteroids and planets forming around stars, there's so much variation, so many different outcomes possible depending on local conditions, that every new object we study teaches us something. 3i Atlas is teaching us that comets from other star systems can have subtly different chemistry, that charge exchange X-ray emission is detectable and informative, that our models of cometary composition need to account for a wider range of initial conditions. Those lessons are more valuable than any speculation about alien probes, because they're real, they're supported by evidence, and they expand our actual understanding of the universe rather than just our imagination. Feel that pull? I do. Every time I look at a plot of the XRISM spectrum with those emission lines standing out like peaks on a graph, I feel a connection to something larger. The universe just got a bit more personal, a bit more knowable, because we took the time to look carefully, to build instruments sensitive enough to catch these faint whispers, to analyze the data with rigor and care. This is what I love about science. It's not cold or distant, it's intimate. It's about paying attention to details, about listening to what the cosmos is telling us, and then sharing that understanding with anyone willing to listen. And what the cosmos is telling us through 3i Atlas's X-ray spectrum is that out there, around other stars, in clouds of gas and dust we'll never visit, similar processes to those that formed our solar system are happening, but with variations. Those variations produce diversity, and that diversity is something to celebrate, not fear. Every interstellar visitor that shows up carrying a slightly different chemical signature is expanding our view of what's normal, what's possible, and what the galaxy contains. We're building a catalogue, observation by observation, spectrum by spectrum, of the rich tapestry of planetary system formation. And this X-ray spectrum from 3i Atlas is one of the most detailed threads we've woven into that tapestry so far. But a single observation, no matter how good, is just a starting point. The real power comes from what we do with that information, how we build on it, and where it leads us next. This X-ray first, this breakthrough observation of 3i Atlas, opens doors that go far beyond just this one comet. Think about what we've established here. We've proven that X-ray observations of interstellar objects are feasible and scientifically valuable. We've demonstrated that charge exchange produces detectable signals that carry information about composition and outgassing. We've shown that instruments like XRISM have the sensitivity and spectral resolution to capture meaningful data from faint transient targets. All of that translates into capabilities we didn't have before. Tools we can now apply to future visitors, questions we can now ask with confidence that we'll be able to find answers. The implications for future study are immense. Every interstellar object that passes through our solar system from now on is a candidate for X-ray observation. We know what to look for. We know how to interpret the signals. We know roughly what exposure times and pointing strategies work. That knowledge will go into planning future observations, refining techniques, and building even better instruments. The next generation of X-ray telescopes, whatever they are, will be designed with interstellar object studies in mind, informed by what XRISM discovered with 3i Atlas. That's how science progresses, each success building the foundation for the next advance. But the impact goes beyond just interstellar objects. The charge exchange technique that revealed 3i Atlas's composition in X-rays can be applied to solar system comets too. In fact, it has been, but now we have a point of comparison. We can take X-ray spectra from local comets and compare them to the 3i Atlas spectrum, looking for similarities and differences that tell us about the diversity of comet formation conditions. Are all comets in the Kuiper belt similar in composition? Do Oort cloud comets differ? And how do both groups compare to interstellar visitors? These comparative studies will refine our understanding of where and how different populations of small bodies formed, helping to reconstruct the early history of our solar system and others. There's also a timing element that makes this moment particularly significant. 3i Atlas is still moving through the inner solar system. It passed close to the Sun, and now it's heading outward, making its closest approach to Earth and then continuing toward a Jupiter flyby. Each of these close approaches offers opportunities for different types of observations. Ground-based telescopes are tracking it in visible and infrared light, measuring rotation rates, surface composition, outgassing variability. Radio telescopes might detect molecular emissions, and space-based platforms, if they can spare the time, could take additional X-ray or ultraviolet observations to see how the comet's behavior changes with distance from the Sunday. This coordinated multi-wavelength campaign is the ideal way to study any astronomical object. No single wavelength tells the whole story. Visible light shows you the dust and reflected sunlight. Infrared reveals temperature and thermal emission. Radio detects specific molecules. Ultraviolet catches certain atomic transitions. And X-rays expose high-energy processes and charge exchange. Put all those pieces together, and you get a complete picture that none of the individual observations could provide alone. XRISM's X-ray data is one piece of a much larger puzzle, and as researchers combine it with observations from other telescopes, the full story of 3i Atlas will emerge in richer detail than we could achieve from any single dataset. The close approach to Earth is particularly exciting for amateur astronomers and the public. At its brightest, 3i Atlas might be visible in binoculars or small telescopes from dark sky locations. That means you, personally, could go outside and see this interstellar visitor with your own eyes. Photons that bounced off a comet from another star system, entering your pupils and forming an image in your brain. That connection, that personal experience of seeing something astronomical for yourself, is powerful. It transforms abstract science into tangible reality. It's one thing to read about an interstellar comet. It's another thing entirely to see it moving against the background stars, knowing that this faint, fuzzy patch has traveled light years to reach your backyard. As 3i Atlas continues its journey, eventually swinging past Jupiter's orbit, it will begin to fade and recede, moving back out into the darkness of interstellar space. This is a one-time visit. It's not in orbit around the Sunday. Its trajectory is hyperbolic, meaning it's going fast enough to escape the solar system's gravity and return to wandering the galaxy. Within a few years, it will be too faint for even professional telescopes to track. It will disappear from our view, continuing its journey to wherever gravity and momentum take it next. Maybe in millions of years, it will encounter another star system, and if beings there have developed astronomy, they'll get to study it the way we're studying it now. Or maybe it will drift through the void for billions of years, a frozen relic carrying the signature of its birth star, untouched and unobserved. That sense of fleeting opportunity adds urgency to the observations. There's a narrow window when an interstellar object is close enough and bright enough to study in detail, and that window is closing. Every observation that doesn't happen now is a lost opportunity. Data we'll never be able to collect from this particular visitor. That's why teams like JAXA's XRISM group act quickly when opportunities arise. They understand that in astronomy, timing is everything, and second chances are rare. The JAXA team, in their public communications about the observation, emphasized its revolutionary nature. This is not hyperbole. It is genuinely the first time an interstellar object has been observed in X-rays with enough sensitivity and spectral resolution to extract detailed compositional information. That's a revolution in technique, in capability, and in understanding. The word revolutionary gets thrown around a lot in science journalism, often applied to incremental advances that are interesting but not paradigm-shifting. This is different. This is opening a new observational window onto a class of objects that we barely understand because they're so rare and fleeting. That's genuinely revolutionary. And importantly, there's no threat. Let me be absolutely clear about that, because whenever interstellar objects make headlines, there's a subset of people who worry about impacts or dangers. 3i Atlas poses no threat to Earth. Its trajectory is well understood, tracked by multiple observatories, and there is zero chance of collision. It's going to pass by at a safe distance, close enough for good observations, but far enough that there's no risk whatsoever. This is pure discovery, pure science, with no danger or downside. Just the joy of learning something new about the universe. But that glow from the X-ray observation, that spectral signature captured by XRISM, lingers in the minds of researchers and enthusiasts alike. It's not just data. It's a reminder that we live in a time when we can actually study objects from other star systems. For all of human history until recently, interstellar space was unreachable and unknowable except through theory. We could study our own solar system. We could observe distant stars and galaxies. But the space between stars, the objects drifting through that void, those were beyond our reach. Now they come to us, and when they do, we have the tools to study them. That shift from theoretical to empirical, from guessing to knowing, is profound. It also raises the question, what else hides in X-ray silence? How many other phenomena in the universe are invisible in the wavelengths we commonly observe but glowing brightly in X-rays or other exotic parts of the spectrum? Every time we develop a new observational capability, we discover things we didn't expect. Radio astronomy revealed pulsars and quasars. Infrared showed us dust-obscured galaxies and young stellar objects. Gamma-ray observations found bursts from distant cosmic catastrophes. Each new wavelength opened a new chapter in our understanding. X-ray observations of interstellar objects might seem like a small niche, but they're part of that larger pattern of expanding what we can see and therefore what we can know. Looking ahead, there are missions in development and being proposed that will have even better X-ray capabilities than XRISM. There are plans for larger collecting areas, better energy resolution, faster detectors that can track variability on short timescales. Each improvement will make observations like the one XRISM performed on 3I Atlas easier, more detailed, and more informative. Eventually, X-ray observation might become routine for interstellar visitors rather than a special achievement. And when that happens, when we have X-ray spectra from dozens or hundreds of interstellar objects, we'll be able to do statistical studies that reveal patterns and trends invisible in small samples. Imagine a future where we can say with confidence that interstellar comets from metal-rich stars have different compositions than those from metal-poor stars, where we can trace the chemical evolution of the galaxy by studying the visitors that wander into our neighborhood. That future is being built right now, one observation at a time, starting with breakthroughs like XRISM's X-ray image of 3I Atlas. The bigger shadow this observation casts is one of possibility, of potential, of doors opening onto new areas of research that will keep astronomers busy for decades. And all of it stems from that decision to point an X-ray telescope at an interstellar comet and see what happens. Simple in concept, profound in impact, that's often how the best science works. But for all these implications and future possibilities to matter, we need to connect them back to something personal, something human, something that reminds us why we care about distant comets and invisible light in the first place. From Japan's Mission Control Room, where engineers monitored satellite telemetry and scientists analyzed incoming data, to your screen right now, wherever you are in the world, this X-ray glow connects us all to stars unknown. It reminds us that we're part of something vastly larger than our individual lives, our cities, our planet. The cosmos isn't something separate, something out there that has nothing to do with us. We're embedded in it, made from it, connected to every star and galaxy by threads of physics and chemistry that stretch across space and time. When I think about the people who made this observation possible, I'm struck by their dedication. The engineers who designed XRISM, spending years solving technical problems, ensuring every component would work in the harsh environment of space. The scientists who wrote the proposals, making the case that observing an interstellar object in X-rays was worth the investment of precious telescope time. The data analysts who processed raw signals into meaningful images and spectra, applying corrections and calibrations, ensuring every photon was counted accurately. The theorists who built models to interpret the observations, connecting the dots between atomic physics, solar wind dynamics, and cometary outgassing. Every one of these people contributed to this moment of discovery, and most of them will never be famous, never receive public recognition, but their work matters immensely. Science is a collective endeavor. It's built on the contributions of thousands of people, each playing their part, each adding their piece to the puzzle. The XRISM observation of 3I Atlas stands on foundations laid by decades of X-ray astronomy development, by space missions that came before and learned hard lessons, by theoretical work that predicted what we might see if we looked. No single person or team could have done this alone. It took a community, a global community of researchers and engineers and technicians, all working toward the common goal of understanding the universe better. And now their work is bearing fruit in the form of this historic image and the scientific insights it provides. But it's not just for scientists. This discovery belongs to all of us. Every person who ever looked up at the night sky and wondered, every child who asked why stars shine, every adult who felt a moment of awe at the vastness of space. You're part of this story too. Science is humanity's collective effort to understand reality. And when we succeed, when we make a discovery or answer a question, that knowledge becomes part of our shared heritage. You don't need a PhD to appreciate what it means that we've seen an interstellar visitor in X-rays for the first time. You just need curiosity and wonder, and I believe those are universal human traits. The cosmos shares secrets when we look right. And by looking right, I mean with the right tools, at the right times, with the right questions in mind. For millennia, Humans looked at comets and saw omens or signs from gods. We didn't know they were icy bodies from the outer solar system. We didn't understand their orbits or their composition, but we looked and we wondered, and eventually we developed the tools and methods to answer those questions. Now, we're in a new phase where we can study not just local comets, but visitors from other star systems. And we're finding that the same approach works. Observe carefully, measure precisely, analyze thoroughly, and let the data guide your understanding. 3i Atlas reminds us that the universe is generous with its secrets if we're willing to do the work to uncover them. It didn't hide its X-ray glow out of malice or mystery in the mystical sense. The X-rays were always there, produced by natural processes, waiting for us to build instruments sensitive enough to detect them. And when we did, when XRISM turned its gaze on this interstellar visitor, the secrets revealed themselves. That pattern has played out over and over in the history of science. Nature doesn't lie or deceive. It simply is, and our job is to observe and interpret accurately. There's a particular kind of joy in that, a satisfaction that comes from knowing we're getting closer to truth. Not truth in an absolute philosophical sense, because science is always provisional, always ready to update based on new evidence. But truth in the sense of accurate, testable, predictive understanding of how things work. The X-ray spectrum from 3i Atlas is truth in that sense. It's a real signal, from a real object, interpreted through established physics, checked and verified by multiple experts. It tells us something true about the universe, and that truth is now part of human knowledge forever. Soon, very soon, depending on when you're watching this, you'll have a chance to participate in this story personally. Grab binoculars if you have them, or find a local astronomy club that might have telescopes set up for public viewing. Go to a dark sky location if you can, away from city lights, and look for 3i Atlas. It won't be the most spectacular thing you've ever seen. It'll be a faint fuzzy patch, maybe moving slowly against the background stars over the course of several nights. But knowing what it is, knowing that this faint fuzzy patch has traveled across light years from another star system, knowing that professional telescopes have captured its X-ray glow and decoded its chemical composition, that knowledge transforms the observation into something profound. You're not just seeing a comet. You're seeing a messenger from another part of the galaxy, carrying information about places and times we can only imagine. You're witnessing a piece of another world, another star system, that has come within reach of your eyes and your binoculars. That's a privilege our ancestors couldn't have dreamed of. They saw comets but had no idea some were interstellar. We have that knowledge, and it enriches the experience immeasurably. And here's what makes me smile every time I think about it. Somewhere out there, light years away, maybe there's a star system around which 3i Atlas formed. Maybe planets orbited that star. Maybe on one of those planets, beings like us or utterly different, looked up at their sky and wondered about the universe. Maybe they never knew that one small icy body from their system would eventually be ejected and wander the galaxy. Or maybe they did know. Maybe they watched it leave and wondered where it would go, whether anyone would ever see it again. We're answering that question now. Yes, someone saw it. We did. We studied it. We learned from it. And in doing so, we connected across the galaxy, not through messages or technology, but through the simple act of observing a shared cosmic object. You're part of this story now, not passively, not just as someone reading or watching, but actively. Your engagement, your curiosity, your willingness to spend time learning about this observation, that matters. It's part of what keeps science alive and vibrant. When the public cares about discoveries, when people get excited about learning new things about the universe, that energy feeds back into the scientific community. It justifies funding for missions like XRISM. It inspires the next generation of researchers who see that people care about this work. It creates a culture where understanding the cosmos is valued, and that culture is what enables all the technical achievements we've been discussing. So as you think about 3i Atlas glowing in X-rays captured by a Japanese satellite, remember that you're part of the chain that makes such discoveries possible and meaningful. From the scientists to the engineers to the public who supports and celebrates their work, we're all connected in this grand endeavor to understand the universe we live in. And every once in a while, that endeavor gifts us with something special, something that cuts through the noise and reminds us why we look up, why we wonder, why we explore. This X-ray image is one of those gifts, and I'm grateful to share it with you. But every story, no matter how cosmic in scope, needs a conclusion. a moment to reflect on what we've learned and where we go from here. We've unveiled the X-ray stranger together, you and I, tracing its journey from detection by JAXA's XRISM satellite through the science that explains its glow to the implications that extend far beyond this single observation. We've explored how charge exchange creates X-ray emission, how spectroscopy reveals composition, how this interstellar visitor differs subtly from the comets we're familiar with, and why those differences matter for understanding the diversity of planetary systems throughout our galaxy. This wasn't just about a comet. It was about what that comet represents, a message from elsewhere, written in atoms and light. If this blew your mind even a fraction as much as it did mine, I need you to do something for me right now. Hit that like button. Seriously, click it. That simple action tells me this content resonated with you, and it tells the algorithm that this kind of deep, thoughtful science content is what people want to see. Every like is a vote for more content like this, for going beyond surface-level facts and really diving into the wonder and implications of what we're discovering about the universe. So thank you, if you've already liked, and if you haven't, pause right here and do it now. I'll wait. Now, here's where I really want to hear from you. Drop a comment below with your wildest theory about 3I, Atlas, or interstellar objects in general. Where do you think this comet came from? What kind of star system do you imagine formed it? Do you think we'll ever identify its origin, trace its trajectory back to a specific star? Or what do you think the next interstellar visitor will reveal? I read every comment, and I love seeing your ideas, your questions, your perspectives. The conversation doesn't end with the video. It continues in the comments, and some of the most interesting discussions happen there, so jump in and share your thoughts. If you're not already subscribed to this channel, what are you waiting for? We're going to be following 3I Atlas through its flyby of Jupiter, and I'll be covering the latest observations and discoveries as they come in. There's going to be more data, more insights, maybe even more surprises as other telescopes contribute their observations. You don't want to miss those updates. Hit the subscribe button, and make sure you've turned on notifications so you're alerted when new content drops. We're in the golden age of astronomy, with new discoveries happening constantly, and I'm committed to bringing you the most interesting, most thought-provoking stories as they unfold. Here's a question I want you to think about, and maybe answer in the comments. Where will you be watching 3I Atlas pass? Are you in a location with dark skies where you might actually see it? Or are you stuck in a city where light pollution hides all but the brightest objects? If you can get out to observe it, will you? Is this something you drive a few hours for, to stand under dark skies and witness an interstellar visitor with your own eyes? I'm curious about your relationship with the night sky, how accessible it is for you, and whether discoveries like this motivate you to seek out observing opportunities. Share your story below. Are you a seasoned amateur astronomer with a backyard telescope, or someone who hasn't looked at the stars in years but feels inspired by this? Both perspectives are valid and interesting. The beauty of a discovery like this is that it works on multiple levels. For professional astronomers, it's a technical achievement, a source of data that will fuel papers and PhD theses, that will refine models and inspire new observational campaigns. For educators, it's a teaching opportunity, a way to explain spectroscopy, solar wind, planetary system formation, all grounded in a real, current event. For space enthusiasts, it's another piece of the puzzle about interstellar objects, adding to the story started by Oumuamua and Borisov. And for the general public, for anyone who's ever felt wonder at the night sky, it's a reminder that we live in an amazing universe full of surprises, that science is actively discovering new things, and that we're all invited to be part of the journey. That's what I try to create with this content. A space where all those levels can coexist, where I can go deep enough to satisfy people who really want to understand the details, but stay accessible enough that someone with no science background can follow along and feel the wonder. It's a balance, and I don't always get it perfect, but I keep trying because I believe science communication matters. The discoveries being made by researchers around the world are too important, too beautiful, too meaningful to stay locked in academic journals. They belong to everyone, and my job, the way I see it, is to help bridge that gap. So when XRISM captured that X-ray glow around 3I Atlas, it created an opportunity. Not just a scientific opportunity, though it certainly was that, but also a communication opportunity, a chance to share something genuinely new and exciting, to explain why it matters, to connect it to broader themes about our place in the universe. That's what I hope I've done here. Not just listed facts, but told a story, painted a picture of the process and the people and the implications, made you feel something about this discovery, because facts alone are dry. It's the context, the meaning, the human connection that makes science come alive. Together, we chase the glow. That's not just a poetic phrase. It's literally what we're doing. Astronomers chase faint signals, trying to tease meaning out of photons that traveled across space to reach our detectors. Science communicators chase understanding, trying to translate technical knowledge into language and narratives that resonate with people. And all of us, anyone who looks up and wonders, we chase that feeling of connection to something larger, that moment when the universe reveals a secret and invites us to understand. 3i Atlas provided one of those moments with its X-ray glow, and there will be more. There always are. The universe is generous that way, constantly offering new phenomena to study, new questions to answer, new wonders to marvel at. Our job is to pay attention, to look carefully, to think deeply, and to share what we learn with anyone willing to listen. That's the cycle that drives human understanding forward, generation after generation, discovery after discovery, each one building on what came before. So as this video comes to a close, as I fade to stars, and you return to whatever you were doing before this journey we took together, carry this with you. You witnessed something historic. You learned about the first X-ray image of an interstellar object, captured by human ingenuity and revealing secrets written in atoms. You're part of the small fraction of humanity that knows about this discovery, that understands its significance, that feels its wonder. That knowledge is a gift, and what you do with it matters. Maybe you share this video with someone who'd appreciate it. Maybe you go outside tonight and look up, seeing the stars a little differently now. Maybe you dig deeper, reading the actual scientific papers, following the researchers involved, learning more about X-ray astronomy or cometary science. Whatever you choose, you're carrying the torch of curiosity forward, and that's exactly what we need. Until next time, keep looking up, keep asking questions, keep seeking wonder in the cosmos. There's so much out there waiting to be discovered, and every single one of us has a role to play in that grand adventure. The X-ray glow of 3i Atlas was just one chapter. The story continues, and I'll be here to share it with you as it unfolds. Thank you for watching, thank you for caring, and thank you for being part of this community of curious minds. Now go forth and chase the glow, wherever it leads you.